Hello everyone, welcome to the Mining Match. So we begin by mentioning our sponsor, Spanomine. If you are in the mining industry and you speak Spanish or you work in Latin America or you're looking to do business in Latin America, you should join Spanomine. They provide professional development and connection in the Latin American community. Okay. Today, we're going to talk about something very important when it comes to mining. You know, we miners work with rocks all the time. We are on the rocks, digging the rocks, or inside earth under billions of tons of rock. And we need to know the property of the physics of how these rocks are behaving over time and how we can optimize and be safe, especially safe, because we risk our lives going into an underground scenario or being next to an open pit scenario. And the rock mechanics is a very important part of doing mining. So our guest speaker today is Dr. Mahabadi. He will explain about what he does in his company to help miners to model rock mechanics. Hello, Omid. How are you today?
Hi, Alan. Thanks for the introduction. Really appreciate it.
Welcome.
Hi.
All yours.
All right, perfect. So thanks again, Alan, for the opportunity to present today. It's a great honor. So I'll start by going to share my screen. If that's okay with you, Alan?
Yes, please. Go ahead.
Okay.
Thank you.
And I'll stop my video just to make sure that we're not putting a drag on the network. So I hope that everyone is seeing my screen right now.
Yes, it's all.
Okay,
just maximize, please.
Yeah, I will do that in a second. Perfect. Okay, so good afternoon or good morning, depending on wherever you are. My presentation today will be a very, general overview of rock mechanics modeling with special application in mining. Before I dive into the presentation, I would like to introduce myself and the company I work with. My name is Omid Mahabadi. I hold a PhD in civil engineering from the University of Toronto in Canada, with a degree in civil engineering, but specializing in computational and experimental rock mechanics. And ever since graduating from the University of Toronto, together with a few other research fellows, we co-founded Geomechanica, where our mission has always been to solve challenging rock mechanics problems through the development and application of state-of-the-art numerical simulation methods. Just very briefly, because I would guess that most of you don't know who we are. At the core of what we do is the Irazu geomechanical simulation software, which solves complex rock mechanics problems using cutting-edge, high-performance computer simulations. Irazu could be applied in various domains, including civil engineering, mining, petroleum, as well as research and development. Today, I will mostly focus on the mining side of things. Using Irazu, we provide consulting services where we, run customized simulations and analysis. In most cases, where conventional tools fail to predict what's happening or, capture the physics behind a problem. These will be the same set of domains that I mentioned for the Irazu software in the previous slide. And finally, we offer rock mechanics laboratory testing, mostly for civil and mining projects, where we test for strength, elastic properties, hardness, and so on. So very much classical rock mechanics testing. So why did we start, developing our own simulation tool? This was mostly due to the limitations of conventional software packages, which could be numerous depending on what kind of conventional simulation tool you look at. But what's mostly common between most of them is that they neglect brittle fracturing and progressive damage in the rock, which we know plays a key role in, let's say, the performance of, for example, open pit slopes or underground excavations. In mining, there are cases that we want to avoid fracturing and damage, but there are cases that you want to damage the rock. When you're blasting or you're caving, you want the rock to fracture preferably. So it's of paramount importance to be able to model fracturing accurately and precisely. Another limitation of conventional tools is that they can usually incorporate a limited number of joints and faults, bedding planes, and so on, or other discontinuity surfaces. And for those of you that have been in the field, you would know that these discontinuity surfaces usually play a controlling role and a decisive role in the performance of the structures, either even underground or surface mining operations. In addition, some of the conventional tools, such as the finite elements method, they assume they can only handle small displacements, and usually they will have issues to capture displacements that are in the orders of meters or tens of meters. And in most cases, risk analysis is only available to look at hazard only, so you see if something is going to become unstable or not, or yield or not, but you can't really get any sense of what happens after instability, so you don't really know the consequence of failures. So with that, this was the motivation for us to develop the Irazu tool, which is a versatile 2D, 3D finite discrete element software package for the analysis of large deformations, fracturing, and stability in rock masses. At a glance, Irazu integrates various multiphysics solvers and advanced features into a single software package that allows us to use Irazu for a very wide range of geoengineering applications, including underground excavations, slope stability, tunneling, dynamic analysis, mining, and reservoir geomechanics. So on a very high level, if we wanted to highlight three of the most important features of Irazu, I would say one is high performance computing thanks to GPU graphics processing unit computing, which allows the simulations to run very fast for comparable software packages that have this same level of physics. It's also quite easy to use because we've developed our own user interface from the ground up, and we have very open input and output file formats that allow you to manipulate the files in any way you want. As I also mentioned, we have multi-physics solvers that allow us to simulate coupled fracturing, mechanical, hydraulic, and thermal processes with realistic rock mass representation. And finally, you're just going to use a single software package for all your geomechanical simulation needs because we're mixing the finite element and this discrete element formulations. So rather than having to buy 3 or 4 different software packages, you'll just have one package that could help you analyze a very wide range of geomechanical problems in mining, civil, and oil and gas. So with that, let's just look at some applications, because that's always more fun. And as I said, this presentation is very high level. So if anyone is interested in to learn more about the physics behind the code, that would be in a separate presentation. So the first example is a surface mining example, looking at an open pit mine where we were interested in analyzing the stability of the open pit slopes as well as the performance of cutbacks. So here, what was the challenge? The main challenges were that this was a large open pit mine that was undergoing significant wall deformations and instabilities. The system behavior was very complex and was characterized by an interplay of major discontinuity surfaces, including faults and foliation, as well as groundwater flow. We had to back analyze it initially to understand what was causing the deformation and failure. So understanding the deformation and failure mechanisms, of the open pit and to calibrate the models for subsequent forward analysis of future cutbacks. So we not only had to back analyze, we had to provide predictions of what will happen in the following stages of the mine design. And in this case, the client came to us because conventional tools had failed to correctly capture the main processes involved, mostly because they require numerous simplifying assumptions, or they don't have the right formulation to handle a system as complex as this. So what was the solution? We used Irazu, which is well suited to analyze the mechanical behavior of rock slopes. Irazu allows us to capture a wider spectrum of slope behaviors without the need for complex constitutive models. So we could very easily capture, continuum deformations, fracturing, complex kinematics, and large displacements. In this case, we had a complex geological model, structural geology model, that was developed by previous consultants, and there were a large number of faults and other discontinuity surfaces that needed to be incorporated because we knew that they're going to play a key role. So these were all digitized and embedded into the mesh for the analysis. You see the picture on the right. And also we included groundwater pore pressure effects to get the effective stresses. And also we took into account coupled flow of water or groundwater through rock fractures. So with this, we were able to successfully back analyze the wall deformations of the current cutback and get realistic deformations and acceleration patterns that matched really well the field observations that the client had gathered over the time, including radar readings, extensometer data, as well as prism data. So, where we see the deformation that you see on the right-hand side, the extent of deformations and the acceleration patterns, they all match pretty well with field observations. With these, we were able to quantify the effect of pore pressure on the slope performance, and we confirmed that groundwater flow through the faults was the main reason that we were seeing large deformations on the slope. It wasn't really groundwater flow in the slope itself, but mostly some of these faults that were connected to a water source, groundwater source, they were seeing or causing large deformations on the slope. In addition, we were able to predict the performance of future cutbacks under different geomechanical scenarios, including excess pore pressures, and we were able to provide ranges of expected slope wall deformations. So let's say if groundwater pressure or pore pressure exceeded this much, this is the amount of deformation that you could expect. And there were some cases that with a half an MPa excess pore pressure, you could see displacements of over 10 meters in some areas of the walls. With these, we were able to suggest remediation strategies such as dewatering campaign to further stabilize the slope, thus cutting the costs and increasing mine safety. So now let's go underground. I have one or two quick examples here that I would like to share with you. The first one is just a blast tank cave, where we look at the cave development and analyze the surface subsidence. So in this case, we have 3 blasts over 5 panels. So we have these rectangles or 5 panels where we are going to simulate ore draw in a caving operation. There are 3 lines on top of each of these panels. We are going to blast these by applying a blast wave pressure profile. That was kind of like mimicked what could be recorded in the field. We also incorporated 2 joint sets, as you see with this, red or yellow lines. So these joint sets were generated using a built-in discrete fracture network generator feature of Irazu. And we modeled variable ore draw from these 5 draw points, as you see here. So it's very easy for us to, just toggle them on or off, say, draw this much material from this time to this time. So as we, started the simulation, Initially, because of the shear, the stress wave or the blast wave, the discrete fraction networks or the joint sets sheared, and there was a little bit more fracturing around the panels. Then this was followed by the excavation of the 5 panels, which resulted in more and more damage. So this animation is unfortunately a little fast, but you see all of these black lines are new fractures that have formed in the rock mass. Okay, and you see bits and pieces of rock that are falling in. We were drawing up until a second ago, and now we're not drawing the rock anymore. So the rock is kind of piling up here, waiting to be removed or excavated from here. So we can very easily model variable or draw. And as you see, there is a significant amount of displacement happening here, in the orders of tens of meters. There's a lot of this, fracturing happening, and you could very easily analyze how much surface subsidence this is going to cause. What was also quite interesting is that in this same example, if you increase the rock mass strength by about 20-25%, you could see how fracturing changes, and you would actually see overhangs forming on the 2 left panels, which is less than ideal, because in this case you want to get as much rock excavated as much as possible, or drawn as possible. The last example that I wanted to show you today is an underground excavation, but looking at the effect of rock support. In this case, looking at rock bolting design. As you see the excavation profile on the left-hand side, and this was in a jointed or discontinuous rock mass, which was characterized by 2 joint sets, as you see, one sub-horizontal and one at about 30 to 40 degrees horizontal from the x-axis. Sigma 1, or the major principal stress, is horizontal in this case. And on the right-hand side, you see the simulation results, so the effect of excavation on an unsupported excavation, right? So all of these fractures and displacements that you see are due to the excavation process, right? So as you notice here, if you do not support this excavation, it becomes completely unstable. As you see, large displacements happening, large blocks of rocks are detaching and falling into the excavation or into the opening, and the velocities are fairly high. So this is, if not treated, this will lead to complete loss of the opening or the excavation. So we started by adding fully grouted rock bolts, and we studied the effect of the increasing of the space in between them. So how many of these rock bolts we have, and as you see, as you increase the number of rock bolts, you are stabilizing the rock mass. So you see the red zones, which are related to zones of higher displacements, are going down, and essentially when you have about 16 of rock bolts here, which is on the very two right-hand side pictures, the rock mass becomes globally stable. There are some local instabilities, bits and pieces of rock that are detaching and flying into the opening, but overall, these are fairly, this excavation remains fairly stable. And I guess with this, you could, use this and, add a secondary type of support, like a mesh or shotcrete, to further stabilize the excavation. So using this kind of analysis, you could very easily predict the performance of your underground excavations and provide recommendations in terms of support design and expected behaviors. So as I said, very quick presentation and high level stuff. So my last slide here is, okay, what is the value proposition here? What are the competitive advantages? So the first one to me is that we have an all-in-one general purpose simulation tool that could be used for the design and analysis of a very wide range of geoengineering applications. Compare this with, having to use 3, 4, 5 different tools for specific applications. And there's, learning and maintenance costs associated with different software packages. So with this, that issue is resolved. Irazu and Geomechanica is developed by a new generation of experts actively pushing the boundaries of commercial geomechanics simulation tools. So these tools have been designed in the past 5 or 10 years. This is spun-off of university research. And that's why the software is based on cutting-edge research and development, both in geomechanics, rock mechanics, and high-performance computing. We're using really state-of-the-art graphics processing unit technology that the kids nowadays are using for Bitcoin mining and blockchain. The same kind of technologies we're now using pretty much for the same kind of hardware we are using to analyze rock masses. So with that, I thank you. As I said, this was a very short presentation, but I'm open if you have any questions or comments. Thanks.
Thank you, Omid. Okay, I'm gonna open the microphones for people to go ahead and ask questions to Omid. If I think you can stop the sharing. So okay. Please, is anyone out in this presentation would like to ask questions? Go ahead. Now is the time. Omid, could you turn on your camera, please?
Sure thing.
Yeah, so here's Omid. Please, waiting for any questions. Don't be shy. You can ask any questions you may have about rock mechanics.
Complex constitutive models in Irazu.
Well, I think that's good enough for questions. And as you know, for you guys that are watching on YouTube and here, this program is also about networking. So you're going to have a chance to talk to Omid directly and just ask about more about his company and their services. And we're going to open the breakout rooms now. So just a very recommendations is that you put your camera, put your speaker so you can speak face to face with the person and allow others to speak. And you're going to have 10 minutes that is counted, it's automatic, and then the room will shut off, okay? And you will be back here for a second round of networking. And you can choose the room where you go, so you have the ability to change. So there's a room called Geomechanica, and there's where you can find Omid. Okay, thank you very much, guys, and I'll start now the breakout room sessions. And for you out there in YouTube channel, thank you very much for watching, and thank you for joining the Mining Match Network. And this program has ended. See you next time.